Everyone, welcome back to the video lecture here for lecture 9, where we essentially started talking about the market structure for duopoly and oligopoly. And this was our first instance of a little bit of a game theory. And so what characterizes this duopoly and oligopoly? Well, for us, we believe that it's the number of size and distribution of sellers, which is different than any other industry. So generally, we say here we have a few firms. So we have 2 to 8 firms controlling roughly 75% or more of the market. But what really defines this is distribution of sellers is the strategic interaction between firms in the industry. And throughout this lecture, we're going to look at a variety of ways that these firms can strategically interact. In terms of the number of buyers, we just assume it to be unspecified, but assume it also to be large. In terms of differentiation, products can be either homogeneous or differentiated. We don't really worry about that so much through our analysis. So you can have oligopolies in kind of commodity goods or things like steel or copper, or you can have, which are very homogeneous, or you can have things that are very differentiated like automobiles or TVs. So what kind of creates this kind of market structure? Well, it also has to do with the idea of entry and exit. So firms in this industry maintain some sort of duopoly in the long run due to some high barrier to entry. It's very similar to what monopolists face, and we realize then if these firms in the oligopolistic industry are facing some barrier to enter or exit, then there must be some sort of market power available to them. So we go a little bit further and we say, in reality, the observables which create a duopoly or oligopoly vary widely by industry and by firm. So we might not always be able to understand essentially why an oligopoly exists, say like the domestic car manufacturers, but we can have some idea as to why they do. And we know that the Department of Justice is very keen on breaking up these duopolies and oligopolies when present. They want to be able to make sure competition is thriving in an industry. So there's 3 different acts that we just briefly mentioned in class. We would go further into these if this was an industrial organizational class, into each one of these acts specifically. But the Department of Justice has a few different tools for themselves to essentially understand how to identify does an oligopoly exist in this industry, one of which is through the concentration ratio. So we have 2 different concentration ratios that we can look at. We have essentially a 4 firm or an 8 firm. And really, the methodology in calculating this is almost identical. The intuition is we want to look at the top firms in the industry, and we want to see if the top firms in this industry essentially provide a significant proportion of the total output to the remainder of the industry. So we look at the top 4 firms or we look at the top 8 firms in terms of the percentage of total industry revenue or market share, and essentially we then divide that through by the total market share. And this gives us some indication as to the concentration of the industry, but it's a little bit misleading because we don't necessarily have any weight given to larger firms in the industry. We could have a concentration of, let's say, 75%, but one firm might be dominating out of those top 4 firms, and those last 3 firms could look very similar to the other firms in the industry. So we get around this in another way. We create this Herfindahl index, and the Herfindahl index essentially is going to highlight firms that are more dominant than others. And the way that we do that is we square the market share for each firm. And once we've squared the market share for each firm, we're going to sum them all together. So when we do that, when we sum all of these firms together, we get a range of values that the Herfindahl index can take on, anchored at 0 and then again at 10,000. And we realize then that a firm that's a monopolist, if their market share is 100%, then 100 squared would be 10,000. So we realize that the 10,000 is attributed to the monopolist, whereas 0 is attributed to the perfectly competitive industry. So how do we then look at the range of values within this index? Well, really anything under 1,000 we deem unconcentrated, meaning that there's a lot of competition that occurs here. If mergers were to take place in these markets, they would go unchallenged by the Department of Justice. They would just let them happen because we realize that there's still enough competition in this industry that the merger won't affect it. But as we look at a little bit higher, between 1,000 and 1,800, we realize that the Department of Justice here might step in and review the merger because they understand that there's going to be some limitations to the amount of competition that we have. So we believe that the Herfindahl index is superior to the standard concentration ratio because it gives a larger weight to firms with larger market shares. So we then here switch gears a little bit to our very first model that's a little bit different than the things that we've seen previous. So previously, we've just been observing profit maximization occurring at where marginal revenue is equal to marginal cost. Well, now in this oligopoly industry, we have a firm that has to make a few different choices, and this is the first indication that this firm is relying on some sort of strategic interdependence. And so the model is called kinked demand. And really what it does is this kinked demand curve tries to explain why we might observe some sort of price rigidity in an oligopolistic industry. And the reason why this is important is because we could see adjustments of marginal cost in this industry, but prices and quantity in the equilibrium remain the same. And so the way that we make sure that this kinked demand curve exists is by looking at a set of demand curves that an oligopolist might face. And so we have a thought process here that we are going to suppose and assume that the product is priced originally at P star. We don't really know how P star exists yet, but let's suppose it is. So now if firm 1 raises the product price above P star, its competitor has essentially two options. They can also raise the price, or they can keep the price at P star, the prevailing price. So if they follow suit, prices is higher, all firms may be better off, we really don't know. But if they hold price steady at P star, then we know the firm 1, which raised their price, will certainly be worse off, and they will certainly lose market share. So now we have a different thought. Suppose that, again, the product price is at P star. Now, if firm 1 lowers the product price to below P star, now its competitors can either follow suit or keep the price at P star. So if the competitors follow suit, all firms will lower prices, assuming they don't want to essentially cede market share. We don't know if they're going to be better off or worse off, or they can hold prices. And if they do, if they hold prices, then they won't sell to anyone in the market since prices are set higher than the competitors. So we have an idea here that firms, when we go back to the picture of this kinked demand curve, essentially at P star, we essentially will follow prices that are higher than us. Right? So we will raise our price higher than P star, and we'll also lower prices when essentially other firms do so. So we'll raise prices when other firms do so, and we'll lower prices when other firms do so as well. So how does that work for us in terms of solving these problems? Well, again, we are profit maximizing, so we must look at the relationship between marginal revenue and marginal cost. But since we have two demand curves, we also will be faced with two marginal revenue curves. Now this is where things get interesting, and that is really marginal revenue and marginal cost can intersect at a variety of different points, but we could still have the same P star and the same Q star. That's different than what we've seen before. We realize that this marginal revenue curve is basically discontinuous. We can't really take the derivative because it doesn't exist at Q star. It's at two different points. So we have to be really careful when we look through, when we look to profit maximize here. So how do we go about solving a problem with kinked demand, essentially? So we must think about some things. We think that intuitively, firms, since they're profit maximizing, quantity will not change in this instance because marginal cost is changing. Firms have less incentive to create more efficient product technologies. That's true. Intuitively, again, with these increases in marginal costs, input prices are rising or could be rising, but they're not necessarily being passed along to the consumer. So if we see that this is occurring, firms don't want marginal costs to rise because they're locked into a price between certain levels of marginal revenue. So with this model, and again, we have yet to describe in any way how the prevailing price is determined, and that's an issue with us. And so we kind of, knowing this, we realize that this model essentially fails to capture real world results because we do know that there's going to be price adjustments that this model can't account for. So in terms of solving a model in this way, and given that we have this kink demand curve, we have to follow a few different steps. So in order to understand what the prevailing price and output level is for a certain product, and so this is problem 10.1 here. So in order to do so, essentially all we're doing is going to set our demand curves equal to each other. And so we could do that by setting 82 minus 88p equal to 44 minus 3p. And all we're saying here is we're looking for the intersection of these two demand curves. So it looks something like this. And so we want this intersection. This will be P star for us. And so we've set these two equal to each other. We could solve down to get something like 38 is equal to 5p, so that P star prevailing price will be 7.6. Excellent. So we have this price. Now we have to determine the prevailing quantity or the equilibrium quantity in this market. But since we're looking at the intersection of both demand curves, it doesn't matter how we take this price, P star, and plug it back in. We're going to get to the same result regardless. So in order to get Q star, I can plug back into either demand curve. And so I'm going to plug into 82 minus 8 times 7.6 so that I get a Q star equaling 21.2. So we'll label these on our little graph right here. So now we have a prevailing price and quantity, and that kind of answers A. So what is our profit then for this firm who's facing this kink demand curve? Well, for us, we know that profit is going to be equal to total revenue minus total cost. And so we can plug in some of the values that we know. So that profit is going to be equal to 21.2 times 7.6 minus, and now we have a total cost function from the problem. We're going to plug that in. So we have 8 plus 21.2 plus 0.05 times 21.2 squared. Now, it's as simple as crunching down the math. So we get 161.12 minus 8 minus 21.2 minus 22.472-ish. So that profit becomes 109.45. So this is our profit at the prevailing price and quantity. So now we go on to answer part C. Part C asks, determine the range of values within which Lightning's marginal cost may vary without affecting the prevailing price and output level. So I think if we kind of punt to the picture here, we realize that we have a marginal revenue curve. That's going to look something like this. So we have this, and then we have something like this. So we have this demand curve, essentially these marginal revenue curves at 21.2. And so we have a prevailing price of something like this. So we have 7.6. Excellent. So now what we're concerned with is this range right in here. So in order to get this range, all we're going to do is plug our prevailing quantity back into each marginal revenue function. So for us, we have to actually create marginal revenue. So I'm going to take the inverse demand for each demand function. So I have 8p is equal to 82 minus Q1. I've already kind of started solving this down so that we have price is equal to 10.25 minus 1/8 Q1. And then I have 3p is equal to 44 minus Q2 2, so that I get P is equal to 14.67 minus 1/3 Q2. So now I have our two demand curves, inverse demand curves. I'm going to solve for total revenue now, so that our total revenue is Q1 times 10.25 minus 1/8 Q1. So that total revenue 2 is equal to Q2 times 14.67 minus 1/3 Q2. So now we know that marginal revenue is equal to the first derivative of total revenue with respect to Q1. So that we're going to get here 10.25 minus 1/4 Q1. And so marginal revenue 2, by taking the first derivative with respect to Q2, we're going to get 14.67 minus 2/3 Q2. So excellent. Now what we could do is we can evaluate them at our quantity is equal to 21.2. So when we do that, we just plug it in. 10.25 minus 1/4, 21.2, so that we get a value of 4.95. And then marginal revenue 2 evaluated at Q21.2. So we get 14.67 minus 2/3 times 21.2. So that we solve down for and we get something about 0.537 or 0.54, however you want to look at that. And so we know now, if we go back up to our picture, that we have some values here. So we have essentially 0.54, and then we have 4.95. So this is the range that our marginal cost can take without changing the prevailing price or quantity. So now the next part asks, based on your answer to part A, what is the firm's marginal cost? Is it consistent with your answer to part C? So we look at the marginal cost given our total cost. So part D is we look at total cost is equal to 8 plus Q plus 0.05 Q squared. And so that we know marginal cost is the first derivative of total cost with respect to Q. So we get 1 plus 0.1 Q. So now let's evaluate marginal cost at Q is equal to 21.2, so that we get 1 plus 0.1 times 21.2, which we get to be 3.12. So yes, we're definitely in our range between 4.95 and 0.54. So then E asks, suppose we have a brand new total cost function. So now we have total cost is equal to 12 plus 5Q plus 0.1 Q squared. Will the firm continue to operate at the same price and output level that we saw prevailing? If not, what will the price the firm charge, and how many units will it produce? Well, I think this is an interesting question. The way that I envision this, and my intuition, is let's first find marginal cost. So we find a marginal cost out of this, and we get 5 plus 0.2 Q. Now my thought is to evaluate this new marginal cost at the prevailing quantity at 21.2. So we'll look at marginal cost at 21.2. So we have 5 plus 0.2, 21.2, and what we end up getting is a value of 9.25 or 9.24. So we realize that that this isn't in our range. And if that's the case, if we're thinking of this, then how do we essentially know which marginal revenue will come into play here? Because again, we have something like this. And again, this is exaggerated, but our marginal revenue, the difference 4.95 and essentially 0.54. So if our marginal cost is somewhere up here, then if that's true, if we had a cost of 9.24, then it must be that we're concerned with this marginal revenue curve. That's what's important to us. So we can go about this. We can actually solve for this marginal revenue, where that equals our marginal cost. So we're assuming this to be happening, or this is our marginal cost curve. So let's look where marginal revenue is equal to marginal cost. And so we're concerned with this 10.25 minus 1/4 Q1 is equal to 5 plus 0.2 Q. So now we solve this down, and so that we get Q is equal to 11.66. This would be our new quantity in this market when we're faced with this marginal cost. So how would we determine price? Well, we knew which marginal revenue function to work with, so we can use that same demand curve. So our demand curve price is equal to 10.25 minus 1/8. Now we're going to plug in our value, 11.66, so that we get a price of 8.79. So this is the new price and quantity at our new total cost function. So then part F says, well, calculate profits based on what you concluded in part E. So part F then, what we're going to do is use our profit function that we already have. So profit is going to be 8.79 times 11.66, this is total revenue, minus our new total cost, which is 12 plus 5 times 11.66 plus 0.1 times 11.66 squared. So we solve this down and we get profit is 102.49 minus 12 minus 58.3 minus 13.596. So that profit is equal to 18.594. Excellent. So now we're able to solve in this way a model of kinked demand. And so we have the written solution next. The next model that we want to essentially work with is something called the Cournot model. Now I think the Cournot model is really interesting because now we have our first model that really worries about what the other firm is doing. So much so that we're including their choice in our response. So this is the beginning of our game theory introduction. So what we are trying to do is look at the interdependence between these two firms. So in the Cournot model, we assume that firms are choosing quantity to maximize their profits based on the assumption that the rival firm will not alter its level of production in response. But they are in some way looking at what they believe the other firm is going to do. But we just assume that once we've chosen, the other firm can't change their production level. So they're kind of locked into some production level here. For this example, for this generalization, we're going to assume that the marginal cost is 0, but that doesn't necessarily have to be the case. We're actually going to solve a problem here where the marginal cost is not 0. So we're assuming that we have two demand curves. And again, what becomes really important here is that now what happens is that for the demand for firm 1, we not only have Q1, but we have Q2 involved. And the demand curve for firm 2 has Q2 like we would expect, but also Q1. So now what we're observing is that a firm is dependent on not only the quantity that they produce, but also the quantity that they believe is going to be produced by their rival, Q2 and Q1. So when we profit maximize, we have to take into consideration that choice from the other firm. So when we create this profit maximization function, all we're doing is plugging into our profit function our demand curve. So what's new out of this is that we've included Q2 for the profit for firm 1, and we've included Q1 for the profit for firm 2. That's unique. This is different than what we've seen before. But in terms of methodology, it's the same process that we've seen in previous markets. We're always using this profit function where marginal revenue is equal to marginal cost to understand where we need to profit maximize. So the next step, once we've observed this, is to actually take that first derivative with respect to Q1 or respect to Q2, depending on your firm. Because that's what you're choosing. If you're firm 1, you can only choose Q1. You only get to observe Q2. And if you're firm 2, you get to choose Q2, but you get to observe what Q1 is. So since marginal cost is assumed to be 0, we essentially can see that these go away, no problem. And so we can solve down again. And what we're going to solve down for now is the decision for firm 1 and the decision for firm 2. And so once we do that, these are our two decisions. And what we call is we have these two reactions. So Q2, the choice for firm 2 is based on what we believe firm 1 is going to do. And the choice for Q1 is now based upon the decision that we believe is going to happen for Q2. So essentially what we're doing here is creating what we call a reaction function. So these two are our reaction functions for each firm. And I think they're interesting because now, and what we're going to do is observe the interaction of these two. What we want to find is an equilibrium. We want to find a point at which Q2 or firm 2, when they choose Q2, doesn't want to deviate given what they believe happened from firm 1, their choice in Q1. And then vice versa, that firm 1 doesn't want to deviate from their choice of Q1 given the action of Q2. And really the only place where this happens is where these two reaction functions intersect. So in order for us to find this equilibrium, what we're going to do is use the substitution method to solve this system of equations. Because now we have two equations, two unknowns. So I'm going to plug in for Q1. So now I have Q2 in terms of just Q2. And I solve down, and I realize now Q2 is going to just be a value. And I can do that similarly for Q1. And so we get Q2 in terms of a value, and we get to Q1 in terms of a value. And in this instance, we realize that they're very similar. They're the same values. And that's because the same setup was used for both firms, 1 and 2. So to better analyze the choices that these firms make, essentially what again, we want to go back to this idea and these reaction functions. Essentially, they show us what our choice should be given the choice of the other firm. And like we described, that the intersection produces this Nash equilibrium. So here is the point at which we're essentially setting equal to each other our two reaction functions. And so we realize that Q2 star and Q1 star come out of setting these two reaction functions equal to each other. And I think this is really interesting. And throughout game theory, we can use these reaction functions to observe what the Nash equilibrium choice should be. So let's solve a problem using the Cournot model. So in problem 10.3, we're given some information. We're told here's our demand curve, 200 minus 2, and then we have Q1 plus Q2. There's some things that we want to identify here. One is that the industry demand is going to be the sum of the two demand curves, Q plus 1 and 2. And so that's interesting because this is going to come into play later on. So now, if we wanted to calculate each firm's reaction function, we could do so by using the information that we have. And the way we do that is start with profits. So let's start with the profit for firm 1. And we realize now the profit for firm 1 is solely going to be based, let's make this a little bit more concrete, is going to be solely based on the quantities Q1 and Q2. So the Cournot model strictly picks quantity here. Prices are going to come afterwards. So we're choosing quantities in this instance. So if that's true, we're going to have our total revenue, which is Q1 times, now we're going to plug in our demand curve that the firm faces, which is 200 minus 2 times Q1 plus Q2 minus, and then we have 4 Q1, which is our total cost. And so now we have a profit function for firm 2, which is, again, going to be dependent on only Q1 and Q2, so that we have Q2 times our demand function, so 200 minus 2 times Q1 plus Q2 minus 4Q2. And we identify that these two profit functions are going to be identical. So let's take the first derivative here with respect to Q1 of profit function 1. And so we're going to set that equal to 0 right away, because if we're profit maximizing, we have to set it equal to 0. So now we have 200 minus 4Q1 minus 2Q2 minus 4. and then we take our derivative of our second profit function with respect to Q2, set it equal to 0 because we're profit maximizing. So we have 200 minus 4Q2 minus 2Q2, 2Q1 minus 4. So let's solve each one individually. We'll label this equation 1 and equation 2, our first order condition 1 and first order condition 2. So our first order condition 1, from this, we're going to solve for Q1. So when we do so, we're going to have 196 minus 2Q2 is equal to 4Q1. So that Q1, in terms of Q2, is going to be equal to 49 minus 1/2 Q2. And so from first order condition 2, what we're going to do is have 196 minus 2Q1 is equal to 4Q2, so that we now have Q2 in terms of Q1, which is equal to 49 minus 1/2 Q1. Excellent. So now here are our two reaction functions. So part B of this problem asks, well, let's solve for some things. Let's solve for what the equilibrium quantity is going to be. Let's solve for what the equilibrium price is going to be. And let's look at the profit for each firm. So in order for us to complete this, what we need to do is use a system of equations. So now we have equations 3 and 4. And so using substitution, I'm going to sub 3 into 4. So that we have Q2 is equal to 49 minus 1/2, and then I'm going to plug in 49 minus 1/2 Q2. So now we have Q2 in terms of Q2. We can solve this down fairly quickly so that we get something like Q2 is equal to 49 minus 24.5 plus 1/4 Q2, so that we have 3/4 Q2 is equal to 24.5, so that Q2 star is going to be 32.67. Now at this point, I realize that our reaction functions are identical. And so what we find for Q2 is going to be the exact same for Q1. So Q1 star is going to also be 32.67. Now this might not always be the case. We might not have the same identical cost curves for each firm, which would result in essentially different reaction functions for each firm. So just be careful as you're solving these problems. It's always useful to go back and solve each reaction function similarly, so we know exactly what the Q's are going to be here. But if you notice that everything is identical, use that to your advantage. Just state that you're doing so. So we could write something like, since the reaction functions are identical, we get. And so we know Q1 star is equal to 32.67. So now, in order for us to move forward, we need to be able to solve prices for us to get profits. So we're going to go back to the demand function. So we're going to realize that P star is going to be 200 minus 2 times the sum of our quantities together. So 32.67 plus 32.67. So that P star is equal to 200 minus 2 times 65.28, or however you want to look at this, to 4. So we have P star is equal to 69.32. Good. So we have now a price and quantities for each firms. So if I wanted to solve now for profit, I'm going to plug everything back into our profit function. So we know that a firm is going to sell their goods for $69.32 times how much they're going to sell for, so 32.67. Essentially, and now what we could do is subtract out the cost. So we have minus 4 times 32.67. So we do this, and profit 1 should be $2,134-ish. And so, excellent. That's what we should find here. And we realize that the profit for firm 2 is going to be identical here, $2,134. And so the other way that we could solve this problem is to actually plug in prices into, we could actually plug into our demand curve, which was in our profit function originally, the 32.67. This is just immediately simplified. Good. So that's how we would solve a Cournot model problem. And so we now, again, want to switch gears a little bit and talk more about a model called the Bertrand model. So the Bertrand model is almost identical to the Cournot model, except for here that firms are choosing prices instead of choosing quantity. So it's essentially that quantity is fixed and that prices are going to be chosen. And so we have the same methodology applying. We should observe that in our demand curve, we should have prices for both firm 1 and 2. And so that we're choosing from our profit function prices, not quantity. And so I think it's really, we could jump right into a problem here because it's the same methodology as the Cournot. So in problem 10.4, what we want to do, we're given some information and we're asked in part A, what is the inverse demand equation of this product? And I think this is an interesting exercise. Okay, so in part A, we know that Q is equal to Q1 plus Q2, so that our industry demand is going to be equal to our individual demand curves. So let's plug those in. So we have 50 minus 1/2 P1 plus 1/4 P2 plus 50 minus 1/2 P2 plus 1/4 P1, so that we get Q is equal to 100. Let's make that 100 minus 1/4 P1 minus 1/4 P2. I'm going to condense this. I'm going to see that there's some like terms, so we're going to take these out. So we have P1 plus P2 here. Great. So the next thing that we need to do is observe. So we need to say that in equilibrium. So in equilibrium, prices are going to be equal to P1, which is going to be equal to P2. And if that's the case, then we are going to say 100 minus 1/4 2P, right? So that we have Q is equal to 100 minus 1/2 P. And I'm going to solve, since this is inverse demand, I'm going to solve for P. So that I get P is equal to 200 minus 2Q. And what we find out is from the Cournot model, this is exactly the same demand curve that we had. We had prices is equal to 200 minus 2 times Q1 plus Q2. So this is the demand curve we face in the Cournot model. So this problem is set up almost identically to what we saw previous. So let's kind of move forward here in part B. So part B is asking us to do all those necessary things. We need to find the equilibrium price, the profit maximizing output levels, and the profits for each firm. So if that's the case, I'm going to start with our profit function for firm 1. So now in terms of P1 and P2, I have the profit for firm 1 being P1 times, now I'm going to substitute our demand curve here, 50 minus 1/2 P1 plus 1/4 P2 minus, now we have total cost is equal to 4Q1. Well, I know what Q1 is, so I'm going to plug this in. So I have 50 minus 1/2 P1 plus 1/4 P2. Now, what I do for firm 1, I'm going to also do for firm 2, but I'm only going to show firm 1 here because everything's going to be identical. So when I take the first derivative, now again I'm choosing P1 because this is for firm 1, setting that equal to 0. What I get is something like 50 minus P1 plus 1/4 P2 plus 2. So I now can take this and simplify to find the reaction function for firm 1. So firm 1 is going to choose P1, and we get that's equal to 52 plus 1/4 P2. So this is the reaction function for firm 1. The reaction function for firm 2 would be identical. So we would have this. So these would be our two reaction functions. Now we're going to solve in exactly the same manner. We have a system of equations. P1 and P2 are our variables, so let's solve. So I'm going to plug one into the other so that I get P1 is equal to 52 plus 1/4 times 52 plus 1/4 P1. So that we simplify, we get P1 is equal to 52 plus 13 plus 1/16 P1, so that we get 15/16 P1 is equal to 65, so that P1 is equal to 69.33. Repeating, and this will be our P1 star, and since we do the same for P2, we get P2 star of 69.33. So here are our prevailing prices in this Bertrand model. How can we use this information? Well, we want to be able to determine what our quantity is going to be. And again, we know what each firm is going to price at. So let's go back to each individual demand curve. So we go back to Q1, but we realize it's going to be equal to Q2, so we just plug this in. So we have 50 minus 1/2 P1 plus 1/4 P2. So essentially what we are going to get is 50 minus 1/2, 69.33 repeating, plus 1/4, 69.33 repeating, so that we get Q star in this market for firm 1 is equal to 32.67. We have Q2 star in this market is equal to 32.67. Excellent. So now we have prices and quantities that are going to prevail in the Bertrand model. And what we say here is that this is a Nash equilibrium. Firms do not want to deviate. This is the best that they can do given what they believe their other firm is going to do. So then the profits for each firm are going to be identical to. So P star is going to be equal to 69.33. The price times 32.67 minus 4 times 32.67. So they get profits for each firm to be 2134.33. So that's the profit for firm 1. The profit for firm 2, like I said, is identical. So we get something like this, maybe some rounding errors in there. But what we find is, I think, something really interesting. So when we go back to the Cournot model, we get exactly the same profit that we did in the Bertrand model. So there's really no difference between the outcomes of our Bertrand or Cournot model. We found basically identical instances. So we realized in the Cournot model, we solved for the equilibrium price of being 69.32. Well, it's exactly what we found that each firm is essentially selling for in our Bertrand model. And we also found in our Cournot model that each firm should be selling 32.67 units. And that's exactly what we find in Bertrand as well. So everything's identical in the setup of these two firms. In the setup of these two models, which I think is an interesting outcome. So moving on from the Bertrand model, we have the idea of a Stackelberg model. And this is a Stackelberg model of quantity leadership. Now let's take some thought, because this is going to be a little bit different from what we saw previously. So what we saw previously is that each firm is going to take the decision of the other firm as given. Well, here this is not the case. We're not going to be doing that. What we're going to be doing specifically is taking the reaction of the other firm into our decision. So now we're not taking the decision of quantity choice as being constant. What we have is we're realizing that a firm has a different reaction based on what we're going to choose. So firm 2 is going to essentially be, we could think of them as the leader, but really what's happening is that they're following, which is weird to think. But firm 2 is going to exploit the decision from firm 1. Firm 1 is going to behave as if they were in a Cournot model, because the firm 1 thinks that firm 2 is just going to also be in a Cournot model. But that's not what's happening. We're going to have not a simultaneous game happening, but we're going to have what we call a sequential game. Firm 1 makes their choice, firm 2 makes their decision. So in order to do this, we need to include that outcome of the reaction function. What we'll understand, or what we'll see, is the first mover will essentially, in this way, or the mover that gets to observe the mover that gets to observe the other firm is going to essentially gain more profit. So how do we kind of think through this example? So suppose that we have this similar, again, this is the identical equation that we saw for the Cournot and the Bertrand demand curve. We also have the same identical total cost functions. So with these, we can start solving the Cournot model for the firm that we believe that is going to be acting as a Cournot. So we already have that information. So firm 1, we're going to say here, is acting as if they are the Cournot player. So it's similar to what we did with the Cournot model. This is exactly what we find. We get their reaction function. But now, since player 2, firm 2, knows that they're playing as a Cournot player, they're going to take into account that idea. So what happens is firm 2 here, and I think this is really interesting, firm 2 is going to take, now, out of their profit function, they're going to substitute in the reaction function. This is the reaction function from the other firm. That's new to us. We haven't seen that before. We've essentially solved for two reaction functions and then simultaneously solved. But here we're going back to the profit function and optimizing given what we believe the reaction is going to be from firm 1. So we do that. Now we solve it exactly how we would before. So we take we have our profit function. We're going to take our first derivative with respect to Q2. And so we now set that equal to 0. So here's our first order condition. And now we get a quantity. And this quantity is really different from what we found before. We found that firm 2, being this kind of, knowing that this is going to happen, knowing that firm 1 is going to be this Cournot player, they take advantage of this and they deviate. And what they do is they get a higher quantity than what they would have done, what they would have made as a Bertrand player or as a Cournot player. And so if we then plug this value back into firm 1's reaction function, we find that firm 1 now is selling less than they would have if they were both playing as Cournot. And so we can sum both of these together in order to get our, total amount of output in the industry. So what does this do? We have a kind of our solution method here. To solve for price, we can substitute Q star into the demand equation. To solve for the profit for each firm, we just substitute each firm's quantity choice along with the industry price. What we notice is the total industry output is higher and the product price is lower for the Stackelberg model than in both the Cournot and Bertrand solutions. That's interesting. What happens here is the firm that isn't the Cournot player in this game, the Stackelberg follower, allowed for larger profits than both the Cournot and Bertrand solutions. Okay, the last little bit that we want to talk about is the idea of collusion. And I think collusion is going to be important as we jump to the next chapter. So collusion is our foundation for a kind of joint maximization of profits. It's where firms recognize their mutual interdependence. And so they coordinate in some way. So they coordinate their output decisions to maximize the output of the entire industry. So we could do this through explicit price fixing, and we could do this through price leadership. One firm deciding on a price and all other firms essentially going through and setting prices to that price leader. Or you can agree to quantity regulations, which is the same, which was what we see with OPEC. So when the agreement is explicit and formal, we define this essentially to be a cartel. And that's exactly what OPEC is that they have an explicitly defined agreement within the oil-producing nations for very specific quantities. Now this is interesting because what happens here in this cartel, since it's illegal, there's no oversight. There's no one actually, there's no one to run to if someone deviates from your existing agreement. So collusive agreements and cartels are really hard to maintain. There's a very high incentive to cheat since contracts in this form are very hard to enforce. Like I said, there's no one to run to, not to mention highly illegal. So collusive agreements are interesting because we're going to act as if we're maximizing one profit instead of two individual profits. So if we were to take the profit function that we've seen from the previous two problems and we sum them together, that's what we're trying to do here. So now what we're going to do is instead of each firm choosing individual quantities to maximize their individual profits, we're going to have one firm act as their benevolent overseer who then decides how much Q1 and how much Q2 to produce in order to jointly maximize profits. And so what we find is that this problem, the solution method, is very similar to what we saw before. So now we're going to take the derivative of our one profit function with respect to both Q1 and Q2 so that we have two first-order conditions. We're going to solve each one of these individually. And if we do so, we're going to solve to get 24.5. So in order for us, we realize we solve these individually, we get 24.5. So combined, the firm or the industry, we're producing way less than we would have in the Bertrand model, in the Cournot model, and essentially in our Stackelberg-Leader model. So what happens, and we also see prices are extremely elevated as well. And that's exactly what we would expect because these firms are acting as a monopolist. So industry profits are almost double, they're more than double, I should say, than what we saw in the Cournot and Bertrand solution. So firms want to act as monopolists and have these collusive agreements together to maximize joint profits. But like we said, it's very hard. So in next chapter, we're going to kind of peel back the layers and analyze kind of the conditions in which it would be beneficial for firms to act jointly versus acting independently.